Louis Laborelli will present for us. He is from the research department at INA, and he has collaborated in many, many European projects in the past. And this time he will tell about this new neural network. Oh, everybody's leaving. Please stay.
Please stay.
It's about a neural network. Neural network that will help us solve problems with SECAM videos and maybe other formats as well. But I think it might be a bit too technical for our crowd.
It's a bit technical.
We'll see, we'll see.
Okay.
Please come in.
We'll see.
I'll open the door so everybody knows that everybody's still invited.
Yeah, I try to speak to the microphone. Okay. Thanks.
Yes, some technicians.
Yeah. Okay, let's start. So, thanks for the introduction. I'm Louis Laborelli. I'm fairly technical, so my talk will be fairly technical. I will start the timing. Oh, wait a second. Oops, wait a second.
He knows himself well, so...
Oh, you stop me at 5 minutes. Okay.
I will.
Okay. So my work is about the improvement of SECAM. SECAM was an old video standard invented by Henri de France, a French engineer, as the name suggests, in the 60s, that was later sold to the East Bloc at that time, and also sold to African countries. So my talk could have been shown in a scientific conference, and in scientific conferences we talk about super resolution with the goal to improve the resolution of video. And in my life as a researcher, during probably the last 20 years, the super resolution was seen as a purely theoretical concept defined by this equation that says that you have an image, it's blurry, and you want to improve, but it was not put into the technical constraints of the degradation of the image. It was a purely abstract thing. So my goal, my approach is to integrate the things into the technical, practical device of the time that were generating the artifacts, and not the purely abstract mathematical definition of the artifacts. So it is a presentation of value. Where was SECAM used, on which kind of step, how was it done, what were the design constraints at the time, what defects were generated by the compromise made at that time, and what can we do now with the full power of artificial intelligence and the result. From an higher point of view, it's a reflection on the evolution of technology over the time, because we have all seen as archivists that we have many eras. So it started with black and white analog video, then we have the era of analog color video, and then the component video, and then the digital video, and then the compressed video, and now we are living in the era of HD. So our customers are waiting for us to give them high quality video using contents from the past. But the problem, the market is giving us new technology every year, but as far as I can understand, there is no compatibility of new technology to the compromise that were taken in the past. I mean, in the past, I will show you some details later. Some compromises were chosen, but when you are introducing a new technology, you don't care about the compromises of the past. And that's the goal of my work. So, a reminder of SECAM. SECAM in French means séquentiel à mémoire. That means that the resolution in color in chrominance is halved. So one line is used for red, one line is used for blue. That means that at each time you are only broadcasting either blue or red, but not both at the same time. That means that the color resolution is reduced by a factor of 2 compared to formats like PAL or NTSC. Why do we care? Because it's still active. In some countries, they are still broadcasting SECAM, as far as from the Wikipedia page. So now they are still using SECAM, but not in France, of course, but it seems that in Africa, they are still broadcasting SECAM. Current user, it seems to be some countries that are still using SECAM, mostly African countries. Former users were mostly in the Eastern blocs, so a lot of countries migrated to PAL first and then to digital, so probably they have still archives in SECAM. Where was it stored? It was stored in 2-inch VTRs that were modified in France for use with SECAM, and also is 1 inches VTR, that is open reel tapes. So the video on the tapes is stored in SECAM format. It's exactly what is broadcasted. Some other VCRs, this time, cassette recorders, are still modified to be used as SECAM, but the format of the video that is stored on the tape is not exactly SECAM. It's called color under, so it's a bit different. It's worse in terms of quality. The 2-inch VTR are storing the full resolution of SECAM. So a refresher, I tried to borrow from courses we were giving internally at INA some years ago. I just added in red. It's complex because we have a path from above that tries to process the luminance, and the problem is that the compromise of that times they were given the instruction to still use the 6 MHz bandwidth of broadcast and put in the chroma in the bandwidth of luminance, which is totally absurd. And they use that kind of coding method to avoid, at least in the best efforts way, the interference between color and luminance. The key word is cross-color. There is luminance that is giving problems in chrominance and the reverse. So there is chrominance problem into the luminance and the reverse. In demodulation, it's more or less the reverse. What is interesting is that compared to other video format, it's frequency modulation, which is interesting because frequency modulation is robust, and that's why it was sold to USSR at that time, because the length of broadcasting was very high. Also, they prefer to have a very robust broadcasting system. And it's interesting for us as broadcaster because it was robust for broadcasting, but it's also robust for storing on tape. But there is a lot of drawbacks. The main drawbacks that in the last 50 years, nobody were able to find a way to separate correctly luma from chroma because of FM. FM, frequency modulation, is a nasty format for separating the color from luminance. And also, there is some variants. Some encoder, it was a copy from a very old documentation. So, for instance, to avoid the artifacts, some encoders, some modulators were using some tricks, for instance, to increase the level of the FM, the modulation carrier, where there was some interference. So, there is SECAM as a format, there is some implementation of format. Not all SECAM are the same, and there are also a lot of variants of SECAM. So what are the impairments? I'm repeating myself. There is chrominance crosstalk, strange color appears due to misinterpretation of high frequency in the luminance. There is a reverse. The color information is eating the luminance, the details of the image. And there is something that is less known, is known only for technicians, is horizontal flicker at about 12 Hz in the vertical direction. So when there is an horizontal line with a color transition, it's flickering. So at that time, the images were seen on the TV screen, very small TV screen, and the TV screen was very blurry and it was filtering a lot of things. Now it's visible, and it's awful. So the spectrum of what was broadcasted, the blue and red line was on the spectrum where the color was put, right inside the luminance information, the detail of the image, which was a bad choice at that time. So the result of that is a very annoying parasite color that was present, and people from my age remember how it was at that time. So it was a simulation I've done with the software. You put a test card, and on the right, you can see that there are two problems visible here. The fine details are translated into strange colors that are moving, by the way. And also, you can see on the top red arrow, on the edges, on the border from one color to another color, the edges are not very good. So if you use artificial intelligence to correct that, it will just enlarge your problem. So it's difficult to see on your projector. It was a simulation I've done of modulated signal. The problem is that the engineers of the time try to hide the problem under the carpet by making things move. And it's a bad decision when we want to compress the signal, because normally the assumption when you want to compress signal by using MPEG is that the still images are still. The decision of that time was to hide the problem by making the image different from one field to another field, because the viewer at the end was human and were not seeing something. So it's difficult to see from your screen. I can see from mine that the two images from a static still card are different. So some tricks were used. It was phase tricks used to hide the problem, to make the problem less visible. And now it makes the problem worse. 60 years after, it was a pattern of variation of phases at that time to make the problem. So it is 1 second before the first color video in France. I took that from the archives. So the luminance it's blurry, but it's not that bad. And when we introduce the color, we get some problem. We get some problem at the edges of the guy. If I enlarge it, you can see on the left, it's the black and white last picture in black and white in France on that channel. The second after is the same picture with color introduced in black and white. I mean, I'm just putting this for what the people have seen on the right. And you can see on the edge, on the black to red edge, that the edge is not perfect. And it's not only imperfect, but it's also moving in time. It's flickering in time. It is the color information that is leaking through the luminance, which is a nightmare. So I talk about color flicker. It's a bit complicated, but what is the result? It is a real image from horizontal white line. If you advance carefully from field to field, you can see flashing colors. It's changing. So at 50 Hertz, it's flickering. At half so it's ugly. It's ugly and it impairs your compression. It's not very MPEG friendly. It's not compression friendly. So when you compare, it's better for robustness. There is a lot of artifacts that were hidden at the time. In PAL world, some colleague of mine at BBC in some European project have proposed a solution for decoding SECAM, decoding PAL that was better than available solution, and they have used that box, they built that box for decoding PAL for archiving. But in SECAM, nothing was available. I've done some experiments on software. It's difficult to see on your screen. a very, very detailed and very colorful image to try to understand what kind of artifact is not visible on your screen, but of course it's blurrier on the right compared to what it is on the left. And you have some artifacts. So in spectral domain, of course, you can see it's a FFT transform of this image. You can see right in the middle the part of the spectrum that is used for coding for colors. So what we have done, now second part of the talks, after the problem, what we have done. We have used digital encoders, the red box, to code a data set into SECAM and use the very advanced blue blocks from Stanley Wilcox to decode it. It's fully digital processing, and we managed to get a data set of 90. We used a data set, very common data set for super resolution studies, of 90,000 sequences, very short. And we have done a processing of this data set, input, output, using SECAM and encoding and decoding. I've built neural networks, which is as input taking a field by field information, 288 lines, 288 lines, and then at the return, I hope to get in, as a result of the algorithms, the interlacing of the video. So I put into the system the fields, and I get result 50 frames per second at higher resolution. So here is the schematics of the PyTorch in neural networks. It seems complicated. It's very simple. So I take as input vertically the current field, the field in the future. I take the result from the past, not only the result as an image from the past, but also the result that was given by the previous action of the neural networks in the past, and also the internal features. And I give the restored image on the top, and also I use back. So it's recursive, it's recurrent in the sense that I reuse what I have done in the past for the previous field. So it's a network that is about 17 million weight. The training was lengthy because it's a recurrent network, and everybody knows in this field that training a recurrent network is slow. It took weeks of training on our machine of 8 GPUs at that time. But the good news is that on current hardware, it's fast. Currently, it's able to process 20 fields per second on a consumer machine that costs next to nothing. So it took 2.5 times slower than real time on one GPU. And it can be probably accelerated in the future. I am in the process of accelerating it. So the result, as a summary, we have improved the sharpness of historical images. We have reduced artifacts like luminance to color crosstalk, the reverse. We have reduced the chrominance flicker. I will show you results. And also we can reduce the noise at the same time. So we are, I hope we have killed at least 3 birds with the same arrow. So the result on the data set, not exactly what the part of the data set that was used for training the neural networks, but the part that was not used. You look at the pink arrow. If there is high frequency information, the high frequency informations get transformed into some strange color. And on the right, you can see that I remove the strange color for text. Same for very, very narrow lines with high frequency. It's very strange, and it's changing from time to time. It's removed. It's more difficult on this screen to see the reduction of color carrier into luminance, but it's visible. Same thing. I don't know if you can see something. Look at the column. There was high frequency. The column were generating high frequency and then colors, and it was removed on the right, and the blurriness was also improved. It's less blurry. Result on the suppression of visible subcarrier. You can see at the transition that it's removed. You can no longer see the FM subcarrier on the luminance on the test card. Same on historical images. So it's less visible here, but it's still. And then the 12 Hz color flicker. It's nasty because it's the color is changing along diagonal lines. The white diagonal lines is no longer white. It's changing from color to color. So that was the original, and now it's restored as the color. The color variation has changed. I'm just showing some three fields, and it's result on the guitar. There was some strange color on guitars moving, and now it's removed. Limitation. It's done on RGB. I should have chosen the way to process everything in original format, but it doesn't matter too much. I've not done training on transition, so I have to verify. The dataset that I have used is a bit suspect because it's called the dataset Vimeo, so it's not very clear if the color definition in vertical direction is good enough, because it was video archive compressed for the internet, so it's not that good. We need probably to improve the diversity of the dataset. And of course, one of the biggest problems is that I have done one experiment with one encoder and one decoder, and I should probably improve the diversity of encoders to take historical encoders and try another. Ongoing work, try to adapt to other video recorders, because for U-Matic, the artifacts won't be the same. Yes, it could be adapted to others. I have to thank my colleague Pascal Flard and Philippe Henry that has done the work. So thanks. I can show the video. I can try to show the video. Okay, so let's try to first by the recent result. So. To start it. It is the result from my process. It took for 10 seconds, like you are seeing right now. It took me 25 seconds. 25 seconds. So it is a result. I cannot show you the original because the original is in JPEG 2000. It was too big to be put on my laptop, but I can show you. I can stop the video. I can show you what was processed using FFmpeg with a very, 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 very slow process using FFmpeg. When I mean very slow, I mean hours for processing. It's crazy. Yeah, it was done with FFmpeg, and it was very, very lengthy, and you can still see the color problem. So the video is not that bad in terms of blurriness, but there is still some color problem. If you apply FFmpeg, you got problem. Here is a comparison of my colleague. I don't know. He compared with Topaz. I don't know if you know Topaz. Topaz is a commercial solution, and it was adapted to interlaced video, but not to SECAM video. So I can show you the comparison of that time. And since Topaz is not trained to SECAM, you will have some problem. I think now it was, in fact, this is a part of the video, it was slowed down, and my process is not able to process slow down video because it's expecting variation of colors. So it's difficult to see on the screen, but the flicker, color flicker is normally better on it's an old version. I think I'm getting better now. of course, nothing is perfect. The net is disappearing. What the net is too small, the net is disappearing. And last video, I think I have one. Yes. For the same program, it will be difficult because it's very high definition video. So, wait. On the middle is mine. My result, I think it's topaz. The original is on the left, middle is mine, and the right is topaz, I think. But I've improved the result right now compared to what it is. To sum up, I've done de-interlacing, removal of color flicker, removal of cross color in both directions, and some denoising. I can stop here, it can be interesting. So the original video, there is a lot of strange problem of colors because it's high frequency information and it's removed. Topaz is not that bad, but topaz is not fine-tuned for SECAM. I don't know how much minutes I have left. I think I'm in advance. I'm speaking too fast. So, so I'm happy to answer any question.
Well, first you get an applause.
Thank you.
Thank you for a wonderful presentation. I think the results are really beautiful. So thank you for teaching us this. Are there any questions from the audience? Yes.
Thank you, Peter from JNM Research. Thanks for the great presentation. So some technical insights. That's always nice to see, to hear.
Thanks.
Yeah, one question. I would be interested on which kind of AI models, deep learning models you started with, since usually it's not from scratch. And if you tested several of them, what were your criteria to select one?
In fact, it is from scratch. I got some inspiration from some other model, but it is from scratch because I am dealing with interlaced video. And most of the model, like for instance Supir, are dealing with progressive video. Recently, I've noticed that, for instance, Disney Research Zurich have done some interesting research that is more advanced compared to what I've shown because the network is a lot more complex to what I have done. They are claiming to have good results, and I believe they have good results because the network is more complex. But the network is not public. The research is public, but the network is not, and they are not adapted to SECAM. So they are claiming to have a good network for de-interlacing, but not for SECAM. But yes, some other researchers are doing great work. My claim is that simple network that is recursive, hard to train, but easy to use at inference, can be useful for the task of SECAM improvement. The network is not that big. For inference, you need only 4 gigabytes of memory, which is nothing.
Okay, thank you, Peter. Are there any other questions? Yes, we have one more.
Have you tried your algorithm on longer sequences, for example, I don't know, minute or more?
Yes. Yes.
And did you experience any problems with like a corrupt image? Because in the typical problem I experience with recurrent networks is that the internal state is like recurrent, it's propagating, yes. And at some point it can like crash, basically leading to some weird artifacts.
We have processed hours of video. We have not seen that many problems. Of course, I've tried other variation. I've tried to, it's not shown in this result. I've tried to use, for instance, if you are a specialist of that field, I've tried to use congru to avoid that kind of problem. It doesn't improve that much. Now I am thinking of using, if you want the truth, I'm thinking of using deformable convolution, attention, and things like that is more modern. What I'm presenting right now is a very, very simple ResNet kind of networks, which is old stuff. I think the state of research right now is more using attention, like in every work in generative video.
Thank you. I was also wondering, what kind of noise did you add to your data? Was it
Gaussian noise.
Okay.
Gaussian noise. And it helps if I train the network by adding noise, the result is a network that will be able to denoise the video. So I have different versions of the networks that are more or less useful at reducing the noise.
Okay. Thank you very much.
Thank you. Are there any more questions? Etienne.
Etienne.
Maybe you could say a few words about how is it going to be implemented into something that is usable easily for the technicians at INA? Because this comes from research. And
the goal is to transfer. That work to operational work. And yes, I have already transferred it to a system. Probably you know more about it. And
don't know anything.
No, but you are from the other side, so you know more about it. Yes, I hope that will be transformed in real production.
Thank you.
Soon. All the things the FIAT IFTA conference is good for. Yeah? Internal communication and implementation.
Yeah.
Very good.
So it's already transferred.
Well, glad that will be saluted. We have time for one more question, if there is any. Otherwise, we'll change laptops again. But first, we give you another round of applause. Thank you, Louis.